Alright, hi y'all. Today we're going to be going over this bounce diagram and snapshot trace problem here. So I guess we can get started. I have some of these equations here that are imperative for this, problem itself. So if you need to, make sure you have them in your crib sheet. So it says a step function of amplitude V naught is equal to 2 volts. So we can write that down. V naught is equal to 2 volts is applied at the input of the transmission line circuit shown below. So we can think of this as some sort of generator. And then we have each of the two transmission lines has a length L that is 3 meters long, so that's important to know also. We have length of 3 meters. Each line has a different effective relative permittivity, however. So we have, we can say ER1 and ER2. Well, ER1 is equal to, and it's effective, we have to, I guess we don't really need to know this, but we have an effective relative permittivity. Okay, this is 4 and this is 9. Well, right away when you're thinking about this type of question, usually they give you the time it takes to go from, source to junction, then junction to load. In this case, they don't give us that. They give us the length and the relative permittivity. Now we need to find that time, the period it takes to go from source to junction and junction to load. How do we do that? Well, if we look here at this equation, we need that is our period. That's capital T. This is the phase or the time shift, that you would see on a V naught, a function, a voltage as a function of time versus time graph. So we need that period. Period is equal to L over CD. Now we know what C is, the speed of light, but we do not know CD. We know what L is, 3 meters. We need to find CD. The equation to find CD is given over at the top of the screen. The speed of light over the square root of the relative permittivity. So what we can do is we can label this CD1 and ER1, and this is 3x 10 to the 8th over the square root of what, 4. And what this gives us is it gives us 1.5 times 10 to the 8 meters per second. Now we need CD2. Hopefully I haven't lost y'all. Hopefully I've explained, why we're trying to find this pretty well. Because we need the period. Because, doing bounce diagrams and we kind of need the period at which, it hits the junction or it hits the load or it's the source. We need to know this. We need to know when the waveform makes these sort of milestones. So we have 3x 10 to the 8th over the square root of 9. And this is equal to 1 times 10 to the 8th meters per second. Perfect. So now what we can do is we can find T1 is equal to 3 meters over 1.5 times 10 to the 8th. And this will give it to us in seconds. So this will be, well, let's see. Let me take mine out of, where's it at? Okay, there we go. So 3 over 1.5 times 10 to the 8th. So that is 2 times 10 to the negative 8th, or 20 times 10 to the negative 9th, which is 20 nanoseconds. T2, 3 meters over 1 times 10 to the 8th. That will be 3 times 10 to the 8th, or 30 nanoseconds. So T2, we need to label this T2 and T1 because right away we know what T1 is. T1 is the time it takes from the source to the junction. But what is T2? Is T2 the time it takes from the source to the load? Well, no, that wouldn't make any sense because that would mean we're mixing our relative permittivities. We want T2 to be the time it takes from the junction to the load. Okay, so that's what we got. We have 20 nanoseconds to go from the source to the junction, and 30 nanoseconds to go from the junction to the load. All right, that's good to know. That'll help us with our bounce diagram a lot, and you'll see how. So, okay, again, the first question asks us to create a bounce diagram, so we can make this upside down box here. And what does the bounce diagram expect of us? Well, it expects a time on the left-hand side And the problem asks, construct a bounce diagram that expects to a time of 50 nanoseconds, labeling with 10 nanosecond divisions. Okay, so we need to do 10 nanosecond divisions up to 50, 10, 20, 30, 40, and 50 here. This is time in nanoseconds. That should be lowercase t. Okay, time in nanoseconds here. And now we know it starts at 0, of course. What else do we need to know of this bounce diagram? Well, we need to know the reflection coefficients at the source and the load, and also we need to know the reflection coefficient at the junction. The reason for this is the characteristic impedances are not matched. If they're not matched, we have reflections, so we need to know the coefficient of reflection. Now we need to solve for these coefficient reflections. So LG, gamma G, is equal to, well, that's Z naught minus RG over Z naught plus RG. I think it's that, right? The impedances don't go last, I think. It shouldn't be. So given that, what else do we know here? Well, we know Z naught is equal to 25 and RG is 25, so this is equal to 0. Now let's look for the coefficient at the load, the reflection coefficient at the load. Okay, so we have Z naught 2, and I forgot Z naught 1 and Z naught 2. Let's label these as 1 and 2 here. It'll help a little bit. Z naught 2 minus RL over Z naught 2 plus RL. I guess I'll see exactly if I'm right or not here. But let's see. So, okay, so Z naught 2 minus RL. Oh, okay. For this one, it's always to the one on the right. My bad. So it's RL here minus Z naught 2 because it's hitting the RL with respect to, Z naught 2, what it was before. So we have 100 minus 50 over 100 plus 50. This is 50 over 150, or 1/3. Okay, now we have the reflection coefficient at the junction. Okay, well, the reflection coefficient at the junction can be two terms, and really we're only looking at the positive, what is going on the right. So where is it going to on the right? Well, just like the load, we need to look at the one that it's going to first. So we take Z naught 2, right? Because you're going from left to right. The waveform is going from left to right. It's going to Z naught 2, so you put that one first. Then you do subtracting Z naught 1 over Z naught 2 plus Z naught 1. What this gives you is 50 minus 25, which is 25, divided by 50 plus 25, which is 75, and that is 1/3 also. All right. And we have to be careful about this because that is the reflection coefficient, yes, but we have to add 1 to it. So T junction plus is equal to 1 plus L junction plus. 1 plus 1/3 is equal to 4/3. So this is what the that reflection value will be. Not the reflection value, but when I draw this, it'll make sense. You need to have that value on the line. Okay, so that's pretty much all we need to know. Let's see, is there anything else? I don't think so. Yeah, I think that's all I need to know. Okay, so knowing this, let's start figuring this out. So we can start here at 0, right? And what I'll do is I'll create a single line in the middle so we know this is the junction. And we know that we start at 0. How far is the junction from the source? Well, it's Z is equal to L, so we put L here. And then from the junction to the load, it's another L, so L plus L, 2L. So now we can create this. How how long does it take for the waveform to get from the source to the junction? Well, it takes 20 nanoseconds. So that's what we should draw. We should just draw a straight line from, and we can label this here, from source to load at 20 nanoseconds. Then what does it do? Well, some of it bounces off, bounces back to the junction, and some of it goes to the load side. So let's go to the load side first. How long does it take for the waveform to get from the junction to the load? Well, we know T2 is 30 nanoseconds, so we can say this is 50 nanoseconds. 20 plus 30 is 50, that's how I'm getting that. So then we can go here to here. And then there will also be some reflection coming back, because there's a mismatch between Z01 and Z02. But how long does it take? Well, to go from junction to source, it takes the same time as it would from source to junction. So what you're going to have is you're going to have this here. You're going from 20 plus 20 to 40 nanoseconds. So this is our basic layout of our bounce diagram. Hopefully this made sense. All I used was the time, the period it took to go from, source to junction, junction to load, and then back from junction to source. All right, so everything over here on this right side will be 0. Okay, well, how do you know that? Well, these lines here, they represent our waveform. If the waveform hasn't crossed, what this area represents is the waveform that hasn't been crossed. Basically, you have to cross over to the left side to get some waveform. I hope you all understood that. So sorry, just know every time that you do this kind of bounce diagram, if you have this empty right side, it will always be 0. But on the left side here, it's going to be something. And we need to figure out what that something is. Now, V0, the V0 that we start with, will not be our original voltage that we see, or that the oscilloscope sees, or whatever, at 10 nanoseconds, 20 nanoseconds. That is the pure voltage source that's being generated from the generator. But it goes through a resistance. And it also goes through this characteristic impedance. Now we need to figure out how much of it is being taken away because of that voltage, or because of that source resistance and the impedance. So what we do is we multiply it by a factor of A, where A is equal to the characteristic impedance of the line divided by the characteristic impedance of the line plus the source resistance. This is equal to 25 over 50, or 1 over 2. So V, I should probably name it something else. Oh, it is V0, yeah. Maybe not V0, we'll call it like the incident wave V+, right? I know they use like reflection as V+, I think, or something, but we'll call this is our incident. It's our incident wave. This is the very first wave that comes out of the, like here. So if we were looking into the, from over here, if we were trying to find the impedance as seen from the junction, this is what we're seeing. Really, that's not, but yeah, sorry, that was confusing. So what we're trying to find is this incident wave, and this is equal to V0 times A. V0 is 2, A is 1/2, so you have a 1 volt. This is your incident wave, I guess, as seen from the junction. The junction sees this voltage. So now what we need to do is we put this incident wave in here, because as the waveform crosses these times and these lengths here, it will the scope will see this 1 volt. It won't see 0 anymore. So everything to the left will get changed unless you cross something like this, or if you cross something like this. So now we need to figure out the values of these lines. If this is 1 volt, because that's what the waveform is. The waveform is 1 volt. So you do 0 plus 1 volt. 0 plus this gives you this. Okay, so now we need to figure out what goes on this line. Well, what goes on that line is 1 times, you take your waveform value and multiply it by the reflection coefficient. So what is the reflection coefficient? This is 1 over 3. So you take the value of the waveform, 1 times 1/3, that gives you 1/3 here. And now you add and cross the boundary. So 1 plus 1/3 is 4 over 3. Now you need to figure out what goes on this waveform. Well, this is your Tj plus. This is, what did we calculate it as? 4 over 3. So now you do 0 plus 4 over 3 is 4 over 3. And we know the waveform is going this way, and this waveform is going this way, because it's bouncing. Okay, so you have 4/3 there, 4/3 here. So let's, clean this up. We can erase some of this stuff here. It's just 4/3, so we can move this over here. And this is also the same thing on this left side of the junction. Sometimes these two sides will not match. That's totally fine. But you have to be wary of that. This is just a coincidence that it did. Okay, so this is our bounce diagram. We're done with this part. Okay, so we've plotted up to 50 nanoseconds, and we can come over here and, oops, let me get this value here. This will be our answer for part A. This is how you construct a bounce diagram, and if you want, you can go to my previous videos. I go into more depth about this. I didn't want to go too into depth about this because this should be, you should know how to make a bounce diagram at this point. And yeah, the junction is still a little weird. It's different for sure, and it does make this look a little confusing because you have this new bounce here. But the only reason there is a bounce there is because the characteristic impedances of our lines here are different. So whenever they see, basically what happens is this line, the impedance that it sees is Z0 and RL, I guess, but it really only sees Z0. That's what it feels, or sees in quotation marks. So if it doesn't see the same value, that means there must be something coming back. It must be a reflection. Anyways, let's go to part B. It says, make an accurate snapshot trace of the voltage on the line at t is equal to 35 nanoseconds. Make your snapshot trace on the graph below, plotting out to L. Label all voltage values on your plot, as well as Z values at which the voltage on your plot changes. Also indicate in which direction, to the left or the right, each wavefront is moving. Okay, so that was a pretty big mouthful, but what all this is saying is make your snapshot, okay? So what you're going to do is come back here, come back to your bounce diagram, whatever you have, even if it's wrong, you have to know how to do this. What you do is, it's at 35 nanoseconds, I believe. Yeah, 35 nanoseconds. So you go to 35, which we can say is around here, and you make a dashed line all the way across. And remember, this is as a function of length L. So we need to figure out at what points, at what lengths did they equal, at 35 nanoseconds. So here it's going to be about, L over 4. Where else does it cross it? Here. This looks about L over 2, actually. Well, maybe not L over 2, but L plus L over 2, which is 3L over 2. So we have L over 4 and 3L over 2. So what is the voltage before L over 4? So voltage L over 4 minus is equal to, what, 1 volt. You see the voltage over here. This corresponds to 1 volt. What about the voltage L over 4 to the right side plus is equal to, let's look to the right, it's 4/3. So 4 over 3 volts. Now let's do voltage of 3L over 2 to the left side. We take our point here, we look to the left, it's 4/3. And now voltage at 3L over 2 plus, we look at our point again where it crosses the waveform, and to the right it's 0. So this makes it very easy, very practical to solve this type of question. As long as you do this, you're going to get full points, as long as you did the bounce diagram correctly. So we come up here and we plot these points. So let's see, VL over 4, or 0, at time 0, from 0 to L over 4, it's 1 volt. So we can make a line here from 0 to L over 4. Okay, that's about straight. Then after L over 4, it jumps up to 4/3, which is 1 1/3. This is 1.5, so we can make it about a little less than 1.5. We can say maybe here. It doesn't have to be perfect, as long as you know that it's less than 1/2. So this stays constant until what point? Well, it stays constant until 3L over 2 on the left side. So you go 3L over 2, which is 1.5. Okay, that's about 3L over 2. And then 3L over 2 to the right side is 0. So we make a straight line down, and we make this all the way to the right, 0. We probably shouldn't. It says up to 2L, so just stop at 2L. Okay, we should label our values here. So this is 1 volt. This is 4 over 3 volts. This is 0 volts. Now, it also says in the problem, it says, label all voltages on your plot as well as all Z values at which voltage on your plot changes. That is another part of the question. Do not forget that. So we know here, or not there. Oops, I totally messed this up. VL over 4 is not VL over 2. My bad. VL over 4 is this here. So this stays straight till there, and this goes down there. There we go. Okay, sorry about that. So this is where it changes at L over 4. Okay, that Z is equal to L over 4. And then it also changes here. Z is equal to 3L over 2. Oops. So that's where it changes, L over 4, because that is our value that we got here and from our bounce diagram. Now it also says, indicate in which direction to the left or right each wavefront is moving. So we come over here, and what we do is we look at which direction the arrow is going on our bounce diagram. So at L over 4, at Z is equal to L over 4 here, on this line that I'm shading in white, which way is the arrow going? Well, it's bouncing off from the right side and going to the left side. So you have arrow going left. So that means you have an arrow going left at your discontinuity. So this is left. Now you look at 3L over 2. Which way is the arrow coming from? Well, the arrow initially goes from left to right, and we don't have any bounces. So it's still going from left to right. So we know it's going to the right. We know the waveform is going to the right. And that's how you do this question. You're pretty much done. That's all you need to do in this one. Hopefully you all understood this. Solving for, these coefficients. This question was a little bit of a longer one, 25 minutes. But if you know how to go straight to the bounce diagram, it makes it so much faster, and you should be able to do this by the time of the exam. If you can't, don't worry about it. Do this work. It will definitely show to be, prove to be useful when you don't mess up the equations. All right, so yeah, hopefully y'all, this is part B here. Hopefully y'all understood this and it was helpful. But that's all I have here. So thank y'all for joining.